Okay, good morning. Hello to everybody. And let us start this lecture. So the lecture of today has as a first topic Landau symbols. Okay, as an introduction, I will tell you that Landau symbols are just symbols that make easier the computation of limits and also give a deeper insight on what limits are. I.e., what I will call the local behavior of a function. Historical remark. Historical remark says that Landau is not, the Landau here is not the Greek physicist, Greek Soviet physicist Lev Landau. He is the small mathematician, who's a German mathematician, Edmund Landau. So if you ever heard of Lev Landau and his very famous books on physics, he's not the guy. The great Lev Landau would never have proposed something like that. He was concerned with great problems. However, so Landau symbols are four. You can find them in books. A first symbol which is a little o, and this is called little o. Another symbol which is a big O, and this is called big O. Then a sort of snake, this is called equivalent. And here you have an equal and a snake, and this is called equi-large. Okay, we will introduce just two of the symbols, no big O and no equi-large. Oh, they will not appear at the exam. But indeed, the little o and the equivalent can be useful. So the first definition is about little o. And as usual, consider a set E R, x bar, which is an accumulation point of V, because we will study a limit, and then two functions f and g from E to R. So we says that f is the expression, the complete expression is little o of g as x goes or tends to x bar, and we will write this, we will write f equal to little o of g as x goes to x bar if, very simple, the limit for x going to x bar of the ratio of f and g is equal to 0. Okay? And the message is that f is little o of g as x goes to x bar means that f is negligible with respect to g as x tend to x bar. So, namely, in a neighborhood, let me say, in a neighborhood in the vicinity near x bar. As an example, very elementary example, consider x bar equal to 0 and f of x is equal to x squared, g of x equal to x, and of course the limit for x going to x bar of f of x divided by g of x, that is equal to the limit for x going to 0 with our choice of x bar over x, which means the limit for x going to 0 of x, and this is equal to 0. So, by definition, x squared is equal to little o of x as x goes to 0. Easy picture that can explain the situation is the following. So here we have the real axis, and so here we have x squared, and here have x. You see here, you have that near 0 x squared is really much smaller, so it's negligible, is much smaller than x. This is very easy to verify, and let me give you another example. X bar has to be an accumulation point of x, so of the domain E. And in this case, we can also take x bar not to be a real number, so x bar is equal to plus infinity. F of x is equal to x squared, g of x is equal to x. So here we have that the limit for x going to plus infinity this time I say g of x over f of x. This is equal to the limit for x going to plus infinity x over x squared, and I can simplify. This is 1 over x. When x goes to plus infinity, this ratio goes to 0. So we can say that g is little o of f as x going to plus infinity. So x is equal to little o of x squared as x goes to plus infinity. wanted to give you this example because see here we have that in the first case x squared is equal to little of x. Here is x, which is little of x squared. But what changes here and where we are looking at the function. Here we are looking at the function near 0. Here we're looking at the function for very large values of x. So what we can see that near 0, x squared is much smaller than x. Here it is. And here near plus infinity. So for large values, of x, it is x, which is much smaller, so negligible, than x squared. This is really elementary, just to get acquainted with this notation. And so another important remark, we will use it a lot. Another important remark is the following, is that f is equal to little of 1 as x goes to x bar, if and only if the limit for x going to x bar of f of x is equal to 0. Why little of 1? Because here little of 1 means that you can write f as f divided by 1, and this goes to 0, f goes to 0 as x goes to x bar. Okay, so f little o 1 as x going to x bar means that the limit is 0, so means that f is infinitesimal as x goes to x bar. And now the important thing is a proposition here. That establishes a relationship between limits and Landau symbols. One has to be careful here because this gives us the language, enables us to describe, to reread limits with Landau symbols. And this is the change of point of view that I want to induce with this lecture. So the proposition says very simply that the limit for x going to x bar of f of x is equal to L if and only if f is equal to L plus little o1 of x going to x bar. So I'm saying that this writing is completely equivalent to this. So in the future, I will often use this writing instead of this. Just a language, but it is another point of view. Limit is something that gives you a number here, and saying that f is equal to the limit plus something negligible. So this is an if and only if, so the proof will consist of two parts. First part, I'm saying that if limit for x going to x bar of f of x is equal to L, this means that the limit of x going to x bar of f of x minus L is equal to 0. Of course, by algebra of limit, I can put this guy here in brackets. And this means, according to the previous remark, that f of x minus L is little of 1 for x going to x bar. So let me write, even though it is a small abuse of notation, but it does not lead to mistake, I can write that f of x is L plus little of 1 as x goes to x bar. End of the proof. What does it mean, L plus little of 1? It means L plus a function which is infinitesimal as x goes to x bar. So it's time for a very well-known example, and we know that the limit for x going to 0 of sine of x over x is equal to 1, and this is true if and only if sine of x over x is 1 plus little of 1 as x goes to 0, and I can multiply by x, and I write the sine of x is equal to x plus x little of 1 for x going to 0. X times a function which is infinitesimal for x going to 0. And now I write here nota bene because it is very important. I'm saying that x little of 1 is equal to little of x as x goes to 0. How can we prove this? Indeed, I want to prove that the function here, the left, divided the function on the right, goes to 0. This is the content. So I write x little o 1 divided by x. This is equal to little o 1 that goes to 0 for x going to 0. So this is true. This is a proof, typical proof with Landau symbols. Therefore, coming back here, I can write that sine of x is equal to x plus little o of x as x goes to 0. And this is the picture here. Here we have the sine, and here we have x. I'm saying here that sine of x minus x is little of x as x going to 0. You can read it an infinitesimal, which is more infinitesimal, which is smaller than x as x goes to 0. Okay, we can also give another example, and then we can go on and on with similar examples. Just the last one for this video is the following. Cosine of x is 1 minus x squared over 2 plus little of x squared as x goes to 0. So we start from the limit, the well-known limit for x going to 0 of 1 minus cosine of x divided by x squared. We know that this is 1/2, and this is true if and only if 1 minus cos x divided x squared is equal to 1/2 plus little o 1 as x goes to 0, if and only if 1 minus cos x is equal to x squared over 2 plus little o of x squared, x going to 0, and this is true if cosine of x is equal to 1 minus x squared over 2 plus Lie law of x squared, as x goes to 0. And notice that, okay, here should be minus, but minus Lie law is equal to plus Lie law, because it is just an infinitesimal. I write it here. Nota bene, Lie law is equal to minus Lie law. No problem with signs and factor. And the picture this time is here. Here you have cosine, and here you have the parabola. So the distance here is Lie law of x squared as x going to 0. And here I stop.